Okay, so we're going to talk about the principle of mathematical induction. Okay, so the idea is you have some statement that relies on, it's a propositional, I guess a predicate is what they'd call it, a propositional statement that relies on the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, and so on. And so we'll call general statement P, and then since they rely on the counting numbers, we'll use these parentheses here, and we'll put whatever number in here. So this could be John has $1. So P of 2 would be John has $2. P of 3, and so on. Okay, so usually we use these with mathematical expressions, like for example, P of 1, or P of, let's do 4. P of 4 means, we're defining the statement to be 1 plus 2 plus 3 plus 4 is equal to 4 times 4 plus 1 divided by 2. Now, in this case, this is actually a true statement, but it doesn't necessarily need to be a true statement for us to use it as a, P of 4 could be false. P of 4 in this case is true. Okay. Now the principle of mathematical induction is, there's a lot to talk about. We're not going to go into everything right now. It is considered an axiom of Peano's axiom. It's the fifth Peano axiom, or it's equivalent to the fifth Peano axiom. And basically it says, if we have the first propositional, the predicate, or whatever you call it, if the first statement is true for the number 1, and then it's also true that if you plug in P of n, if that implies P of n plus 1, if that's also true, if this statement right here as a whole is true, and this statement right here is true, then P is true for all numbers that you plug in here. That's going to be true always, no matter what number you put in here. And what I just said right there, that's the principle of mathematical induction. And so people think of it as dominoes a lot of times, because here's P of 1, here's P of 2, domino P of 2, here's P of 3, P of 4, and da 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 da, and so on. And this part right here that says P of n implies P of n plus 1, that is saying like the distance between these dominoes is short. That if you knock this one over, it's gonna knock over the next one for every single one of these. Then P of 1, if that's true, that's like saying I'm pushing the first domino. So what's going to happen? You know all of the dominoes are going to fall just from that information there. So you don't have to check every single case. You just need to check the first case, and then you need to check the relationship between successive cases. Okay, so we're going to look at an example, and then I'm going to talk about why each is true. Let's look at this example right here. So we want to prove 1 plus 2 plus 3 plus dot 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 plus n is equal to n times n plus 1 over 2. We want to prove that. Okay, so first, let's define P. So P is going to be the statement. We plug in the number 1, that's going to be the statement 1 is equal to 1 times 1 plus 1 over 2. P of 2 will be the statement 1 plus 2 is equal to 2 times 2 plus 1 over 2, and so on. So P of n is actually this whole statement, right? What we have written out right here. That statement will be P of n. And we know that this is true because this is 1 times 2, that's 2, divided by 2 is 1, that's equal to 1, that's true. Let's check P of 2, is that true? So this is 3. And then this is 2 times 3, that's 6 over 2, that's 3. So yeah, P of 2 is true. But we don't know if it's true for no matter what n we plug in. We don't know if that's true. So we're going to use the principle of mathematical induction to prove it. So what we need, we don't even need P of 2. We need P of 1. We need to know if that's true, and it is. Right here, it's true. And then we need to check the relationship between successive statements. So we need to check if P of n is true, if that implies P of n plus 1. P of n plus 1, if that's true. So if this is true, implies that this is true, along with the fact that this is already true, which we found out right here, then it'll be true for no matter what n we use. Now, why is that? Why, if we prove that this is true, this relationship is true, we've already proved that it's true for the number 1, well, then it's going to be true. Well, P of 1 implies P of 1 plus 1 is true, which is P of 2. So now we know P of 2 is true. Well, we know P of 2 is true, so plug that in for n, and that implies P of 2 plus 1 is true, which is P of 3. And then P of 3 implies P of 4 is true, and so on. And so you can go through all the numbers that way. Oops, let's see, undo. I just want to erase this. Okay, so let's go ahead and prove that this statement right here is true, that P of n implies P of n plus 1. Okay, so if this is true, so P of n is 1 plus 2 plus 3 plus dot 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 plus n is equal to n times n plus 1 over 2. If that's true, then that implies that 1 plus 2 plus 3 plus dot 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 plus n plus n plus 1 is equal to n times n plus 1 over 2 plus n plus 1. All I've done is added an n plus 1 to both sides of the equal sign. Okay, now let's take a look at the right side. We make the denominator 2 over here. We have to put a 2 in the numerator. So that's n times n plus 1 over 2 plus 2n plus 1 over 2, which is n plus 2 times n plus 1 all over 2, which is equal to, I'm going to put the n plus 1 first, then this n plus 2, I'm going to write it as n plus 1 plus 1, and then over 2. So this is equal to that, but that statement is P of n plus 1. So we've started with P of n, and we've deduced that if n is true, n plus 1 is true. Okay, so now all the dominoes are falling because we have the first domino fell, and then the relationship is if one domino falls, the next one falls. So all the dominoes fall. Okay, so that would be considered the proof. So let's put a check mark there, check mark there. There's always two parts to these principle of mathematical induction proofs. The first part where you check the initial case, and then the second part where you check the relationship between successive cases. Okay, let's talk about why. I'm just going to give some simple examples as to why each of those cases is needed. Each of these situations, each of these steps is needed. So why is the first step needed? Let's take a look at an example of where let's take a look at an example of where the first, well, why is the second case? Let's look at the second step, why the second step is needed. So we're going to look at an example where the first step is satisfied, but the second step isn't satisfied. Okay, so let's do P of n to be, let's think n squared is less than or equal to 4. Okay, n squared is less than or equal to 4. So let's check P of 1. Is that true? P of 1 would be 1 squared is less than or equal to 4. Yep, that's true. Let's check P of 2. P of 2, 2 squared is less than or equal to 4. Okay, great, that's true. But clearly, P of n does not imply P of n plus 1. And you won't be able to prove that. And then you can see a counterexample as to why it wouldn't be true for all n. If you look at the next number, P of 3. P of 3 is 9 less than or equal to 4, which is false. So P of 3 is false. Okay, so that's why we need the second step. Okay, now let's take a look at a real simple example of why we need the first step. Let's use the statement P of n is n is equal to n plus 1. Okay, so let's skip the first step for now, and let's look at if P of n, so that's step 1, let's look at step 2, if P of n implies P of n plus 1. Okay, so P of n is the statement that n is equal to n plus 1. Okay, but that implies, so P of n implies if you add 1 to both sides, you get n plus 1 is equal to n plus 1, I don't need that, n plus 1 plus 1, which is P of n plus 1. So this is true. This is satisfied. But let's go back. We skipped the first step, and let's try it out. P of 1 is equal to 1 plus 1, which is 2. Is that true? No, that's false. Okay, and matter of fact, no matter what number you put in, P of 7,059 is not going to be equal to 7,060. So that will always be false, no matter what number you put in. And here's another modified version of the principle of mathematical induction. Say you have a statement that's not true for P of 1, it's false. It's not true for P of 2, it's not true for, say, P of up to the first 99. But it is true for P of 100. And P of n implies P of n plus 1 for every n greater than or equal to 100, then no matter what number you plug in here that's greater than 100, it will be true. But all these other numbers that where it's false before 100, they're obviously, well, they're false. Okay. All right, and that's the principle of mathematical induction. One note I wanted to add, but we can't really talk about it too much, is that the principle of mathematical induction is logically equivalent to the well-ordered principle, which kind of shares the seat of the table of the piano axioms as the fifth axiom.